This video will introduce you to some of the basics about forces. The first thing we'll learn about are force diagrams. Force diagrams are a way of analyzing the forces acting on an object. For starters, I have a few examples of some force diagrams. The first force diagram that you see is an airplane, and it shows the four forces acting on an airplane. Those four forces are lift, drag, weight, and thrust. Thrust is the forward force from the engines. Lift is the force from the air going above and below the wings. That's the force that keeps the airplane in the air. Drag is the air resistance acting on the airplane. And weight is the gravitational force. As you can see in this diagram, all four of these forces are represented by vectors, represented as arrows, and the tail end of the arrow is always on the object. That must always be true of force diagrams. Force diagrams also don't show any of the surroundings, just as in this second picture. This first picture in the series of three is a picture of what's really happening. You can see that a man is rappelling off of a cliff. This second picture is the force diagram. We've removed any of the surroundings and we just have the object that we're looking at the forces for. There are four forces acting on this man. The rope is pulling upward. Gravity is pulling downward. Friction is acting upward as his foot slides on that cliff. And we have the cliff pushing on his foot as well. Each of these forces have the tail end of the arrow on the object, and the force points away from it. Also important is that each force is labeled. Drawing force diagrams can sometimes take a little bit of artistic talent. And as we know, physicists are not known for their artistic talent all the time. So they came up with another type of diagram that can be used to analyze the forces on an object. This new type of diagram is called a free body diagram. You may see free body diagram listed as FBD for short. Free body diagrams follow their own unique set of rules. The first rule is that the object is represented by a dot. Also, each arrow, each vector, must begin with its tail end on that dot, pointing away from the dot. You'll see the diagram on the right here is a free body diagram because my object is represented by a black dot at the center. And you'll see that almost every arrow begins on the dot, with the exception of this friction arrow. This friction arrow is in the wrong location. It should really be located with the end of that arrow on the dot, like so. It is okay for these two vectors to overlap a little bit. This next example problem will let us use our knowledge of free body diagrams. It asks us to draw a free body diagram for three objects. We'll start off with the first one. The first one is a projectile in motion in the presence of air resistance. We'll start off with a dot for our projectile. And if we think about what's happening, let's say that our projectile is moving to the right. That velocity vector is not a part of our free body diagram. I am simply using it to help me know how to draw some of the other vectors. So I've kind of put it off to the side. The first vector that I always think about is the force of gravity. Gravity acts on every single object that's on Earth, and it always points straight down. Again, remember that you want to label each vector. And so I'll do so, labeling this as an FG. It does tell me also in this problem that there is air resistance. While we haven't studied much about air resistance, you should know that it acts against the way an object is moving. So if an object is moving to the right, air resistance is to the left. It's just like a wind that you might feel. And so I've drawn my vector pointed to the left. and I will label this as F sub r. It doesn't matter what letter you use. I use R for resistance. That's my free body diagram for this first object. Moving on to B. B is a rocket leaving the launch pad with its engines operating. I'm going to assume that this rocket has just left the launch pad, so it's not touching anything. I'll start off with a dot, and I'm also going to assume that my object is moving upward. Again, the force of gravity acts on this rocket. We'll draw that as a downward arrow, and we'll label that as FG. And then there's also the rocket, the force from the engines. That's an upward arrow. Now you'll notice that I'm very picky about the length of my arrows. That's due to the fact that this force from the rocket must be bigger than the force of gravity, or else this rocket would never accelerate upward. So the force from my engines is a little bit larger than my force of gravity. I don't care about the exact length of them, as long as the relative magnitudes are correct. In other words, as long as the force from the engine is a little bit bigger than the force from gravity. Finally, in part C, it wants to know the free body diagram for an athlete running along a horizontal track. I'm going to say that this athlete is running to the right. Now, you don't always have to draw this velocity vector when you're drawing a free body diagram, but since this problem is not being very specific about the direction of travel, I'm using it to help me draw these vectors and know what direction to put these vectors. So again, the force of gravity acts downward, and we know that that is always the case. And we have a contact point between the athlete's feet and the track. Anytime you have one thing touching another, there is a force there. I will just call that the force from the track, F sub t. There's also bound to be friction. And while we haven't spoken about friction at all yet, it is always against the direction of motion. So if velocity is to the right, friction is to the left. While we haven't talked about it yet, that is the symbol for friction. Okay? There's also going to be some forward force from the athlete's legs moving him forward. I don't care too much about what we call that. I'll just call that F sub F. The forward force from the athlete running on the ground. So hopefully this gives you a little bit of an idea what free body diagrams look like. Next, we're going to learn about some common forces that may appear in your free body diagrams and in problems that we learn about. There are 4 common forces that we will use in honors physics. The first one is the gravitational force. This is a force you already know about. It's the same thing as gravity, the thing that we normally call gravity. And as you know, sometimes it can be equal to weight. Its symbol is Fg. And as we've already talked about, the equation is Fg equals mg. Gravitational force is always pointed directly down. A new force that we have not yet talked about is called the normal force. This is the force that a surface exerts on an object. I consider a surface to be something that is much larger than the object. So, for example, if I set an apple on a table, the table would exert a normal force on the apple. If I had an apple sitting in my hand, I would not call that the normal force. I would just call that the force from my hand. The symbol for normal force is F sub capital N. However, some textbooks will just use a capital N for normal force. I tend to shy away from that because I find it can be confusing for using that capital N for normal force and the capital N for newtons. The direction of normal force is perpendicular to the surface and always pointed away from the surface toward the object. So if I go back to my example where I have an apple sitting on a table, the normal force would be pointed straight up. If instead that apple were somehow affixed to the ceiling, or even were just being held up to the ceiling, the normal force would be straight down. If I'm looking at the normal force on a hanging picture, something that's hanging on a wall, the normal force would be out, away from the wall, toward the picture. So as you can tell, normal force varies in direction depending on the situation. Another common force is tension, and we use a capital letter T for tension. Tension is the force that a rope or string or chain or anything like that exerts on an object. The direction of tension is along the rope, away from the object. So if you had a rope attached to a ball, or let's even say a yo-yo, that might be something you're more familiar with, and the yo-yo were hanging straight down, the direction of tension would be straight up. The final common force is friction. And as I mentioned on the previous slide, we use a script letter F for that. We won't talk about friction in great length in this video. Rather, we'll get to it later in the chapter. The final concept of this video is the concept of equilibrium. And it's a very important concept to us. Equilibrium states that the net force is equal to 0. If an object is in equilibrium, the net force, or the sum of all the forces acting on it, is 0. Well, Newton's second law tells us that net force equals mass times acceleration. And mass can't be 0, or else we wouldn't have an object that we're talking about. So if I combine these two facts, an object that is in equilibrium has no acceleration. An object that is at rest is in equilibrium. But can an object be moving and be in equilibrium? The answer is yes. An object that is moving at a constant velocity, which means that it's moving at a constant speed in a constant direction, is in equilibrium. Because if it has a constant velocity, its acceleration is 0.